Hello. So this is another lecture in lecture series for mechatronics engineers. I'm going to give an introduction to PID controllers. If you're coming from a mechanical engineering or even or electrical engineering background, you already taken at least one course in control, so you're familiar with these things. But I'm gonna review PID controllers and essentially talk about some general things about feedback systems and controllers. Um, if we were to depict a general feedback system, this is how we would do it. You have an input, and then we have a controller, a plant, and an output. And we have a sensor. Ideally, what happens is that we measure the output accurately. In other words, the sensor is able to accurately measures the output. And if the system is linear, and if we were able to accurately measure the output, then the problem becomes pretty easy. So it essentially reduces to the simplest problem and control, because then I have an output and the system is linear. There's a linear relationship, and I have accurately measured output. So I can easily design a simple controller to follow that output and essentially converge to our set point. Now, what I'm going to do here is I'm going to look at the linear system first, and then I'm going to discuss PID controllers. Now, the fact I'm doing it for a linear system doesn't mean it's limited for use to linear systems, but mathematically it would be much easier to show how it works. So, and I'm going to assume that initially, at least, that my sensors are DS sensors. They're able to measure my output accurately. If I do that, then I can simply remove this block, because then what I'm having here on this path, on this feedback path, is going to be equal to actual output. So I'm going to just call this actual output. Otherwise, to model this system more realistically, what I'm going to do is later probably add some noise to this sensor. So I'm going to have some noise sources and then add it to this sensor. So different parts of this system may, if you wanted to model it realistically, would be different. Even like when it comes to controller and our plant, it happens that our plant, for example, has its own disturbance as input. Sometimes we are even after that disturbance, meaning that if we look at for example, the model for an accelerometer, some accelerometers are designed, for example, to essentially characterize that disturbance. That's how they're designed. The set point is, for example, a zero displacement, and then the disturbance comes into our plant, and then in the lecture, essentially I have described the basic structure of an accelerometer, and then you can see what I mean by that. So we design our feedback to bring back the disturbance or reduce the disturbance to zero, and based on the force that we need to use to make that disturbance to go away, in the case of accelerometer, then we estimate the input force, which is related to our input acceleration. Anyway, so this is the simplest model. So I'm assuming that I have a plant and I have a controller. Let me make sure I am in the frame. All right, so I have a plant and I have a controller. Let's say I'm talking about things in S domain. Already used my Laplace transform, and then I've described my plant and my system in S domain. Simply put, we can write down the equation for this system in S domain, and you already know that x out is going to be hk over 1 plus hk as our closed loop transfer function multiplying x in. If you don't recall it, no worries. You can simply say, all right, I have x out here, x out comes here. Then I'm subtracting this x out from x in, multiplied by ks, multiplied by hs, and then it's equal to, again, my x out. And then you can solve for x out and derive this simple relationship in essentially one line. All right. So ideally, if I give you this, what would you say? I mean, if I ask you just what would be our end goal? So I've given this to you, and this is a system. There is a set point. There is an output. I've used in instead of set point. But our goal is to accurately follow our in, right? Meaning that we ideally would like our out to match our in or our set point. So you're going to say that, okay, if hk was much larger than 1, then I would ignore 1, and hk over hk, then x out becomes equal to x in, right? Just a simple explanation. But then h represents our plant. So h most of the time cannot be changed. So you have a plant, you have a system, and your goal is to design a controller for that system. So you have already, the plant is given, h is given. But if I add this block here, my controller block, that's up to me how I design that controller block. And that could be used to essentially and ideally match input or match our set point. So the controller design is a rich topic because of that, right? So we have all these methods to design controllers, and that's what we're going to discuss. So let's say in this lecture, I'm going to go directly to PID controllers. So let's study proportional integral differential controllers. That's where the PID comes from. A PID transfer function in S domain, Ks, is K0, 1 plus beta over S plus gamma S. Right? So you have simply a gain, constant gain, and then you have this term, which represents an integral control. And you have this term, which represents differential control, because it produces controller output proportional. This is proportional. Let me just write it down. Proportional to the rate of change of the error. So if you go back to your basic Laplace transform, you remember that 1 over s represents an integral and s represents differentiation. Right? This gamma is also called rate control. Right? Again, because it produces controller output proportional to the rate of change of the error, corresponding to the factor s in the Laplace transform domain. All right? Okay. And then its most general form, our plant, should be described this way. HS is NS over DS. Makes sense, right? All right, all we need to do is substitute 2 and 3 into 1 to have this closed loop transfer function. So I have now x out, and then I have x in, right? So now the first, we should investigate this step by step. So what I'm going to do is, I'm going to set gamma equal to 0 first. And if I do that, I'm going to have proportional, because I have set gamma equal to 0, I have proportional integral control. I've set gamma equal to 0. All right. And again, this is a reminder that you can use a root locus method to generate the parametric plot of the pole locations. All right. So, and then what happens is it's pretty straightforward. So for each system, you can essentially compute HS, the plant, substitute it in 4, and use root locus method to discuss the stability of frequency response. This is something I'm going to discuss using an example. All right. All right. All right. Let's include the example here in this lecture. All right. I just need to make sure my discussion, my lecture is completely in the frame. All right. All right, PID controller example. So we have already talked about I have essentially characterized our x out versus in proportion to x in. So all I need to do is, I said that we have only 2 steps. We need to characterize or find HS, the plant model in Laplace's domain, or Laplace transform domain, and then substitute that HS into the general form, and then characterize the system output as I vary the controller parameters. So let's say our plant is a spring dashpot mass. All right. Again, if you don't recall like how to derive this, so simply write down mx double dot plus cx dot plus b, I'm using b in this case, bx dot plus kx equal to some external force. Then you take the Laplace transform from both sides, and this is you end up having. So your plant having hs equal to 1 over ms squared, m being the mass, bs plus k. So let's see, this is my mass. Alrighty, this is my mass. This is my force. This is my spring. This is my dashpot. Right? F, all right, and this is X, all right. You write down the equation of motion, the linear equation, take the Laplace transform, and you end up having the transform, the plant transfer function. All right, and then I'm going to normalize this transfer function. I'm going to use normalize S with respect to omega 0, and omega 0 being the natural frequency of undamped system. And I define a quality factor. All right, so this is quality factor. All right, omega 0 over b, b being my damping. All right, this is b and k. Once I do that, for the rest of the discussion, I'm going to assume that k is equal to 1. That doesn't change anything. You can, all right, let me just make sure that I'm completely in the frame. All right, and then you can generalize it for k not equal to 1. Or you can think about it this way. I have already normalized my force, so with respect to my stiffness, so I can assume k is equal to 1. All right, so once I have that, at the end, what I'm gonna assume is my damping. I'm gonna assume that my system is critically damped. Just to recall you, when it's critically damp, my damping is 2m omega 0. So my quality factor is gonna be equal to 1 over 2. All right, so I have one edge as hat, and I'm gonna keep it this way. All right, just so I can clearly and easily identify N and D. If you recall from our general equation, I've used N and D. So all I'm doing is just identify N and D. And once I do that, then I'm going to come here. I'm going to also use a couple other variable changes. So I'm going to I'm going to replace beta with beta hat, and I'm going to use replace gamma with gamma hat. All I need to do is just go back to our general equation, x out and x in, equation 4, and then I'm going to replace N and D with my N and D in this case, or for this plant, and I end up having this x out versus x in. So it's pretty straightforward, right? And now I have this transfer function, and I can study this the behavior of this transfer function when I vary the parameters of our controller. I have gamma hat and I have beta hat and I have k0. Let's say for case 1, I set gamma hat equal to 0. Remind you, gamma was representing our differential controller. So I have proportional integral controller. And then to study, I'm going to assume Q is equal to 1 over 2. It's the plant is critically damped. You can study other cases. And let's use beta hat equal to 1. Again, you can study other cases. So I've used these numbers in this equation, and it simplifies to this equation. So if you pay attention here, my poles, again, going back to root locus method, our goal at the end, not the goal, our method at the end, root locus method says that we are going to plot our poles you're essentially draw a parametric plot when the k0 varies. So if you pay attention, these poles always have negative real part, all right? And so they are essentially stable, all right? So let's see, I forgot what I was going to talk about. Yeah, so in case 2, I'm gonna set gamma hat this one equal. I'm gonna just use a non-zero number, so I'm gonna include my differential control 2. So this is a full PID control. The differential feedback pushes the asymptotic pole locations away from the imaginary axis, stabilizing the system at high gain. All right. So what happens is that if you can try this, you can try for this system, you can go back here, you can replace, for example, gamma hat with for example, 0.1. All right, you can replace gamma hat with 0.1, and then you can try beta hat equal to 1 and quality factor equals to 1 over 2. Again, this is our critically damped plant, and then you're going to see that the system becomes further stabilized when for high gains when you include your differential controller. So what I'm going to do is I'm gonna upload a simple simulation file. They're in Mathematica or Maple that plots essentially generates a root locus plot, for example, for this case, and then you're gonna play with these parameters and see how the poles show up for this system. All right, thanks for paying attention.